Greetings, this is N1IR, and today I'm going to go over the general licensing class G5A through G5C electrical principles. All right, so here's an overall view of the general class element 3, and we're on G5 electrical principles. All right, so electrical principles, impedance, which is represented by Z, is the opposition to the flow of current in AC circuits. So we have R, which is for resistance, and DC, impedance, which is represented by Z, is the opposition to flow of current in AC circuits. Reactance is the opposition to flow of alternating current caused by capacitance or inductance. So when we talk about AC and we talk about inductance, we have inductive reactance, and this formula here, it's equal to 2 pi FL, which is F is frequency, L is inductance. We also have an impedance for capacitance, so that's X sub C equals 1 over 2 pi FC. F is frequency of the circuit and C is the capacitance. When X sub L equals X sub C, it creates a special frequency called resonant frequency. So when we have these two guys together, either in series or in parallel, when X sub L and X sub C are equal, that's our resonant frequency. All right, so to break this down, we have X sub L equals 2 pi FL, X sub C equals 1 over 2 pi FC. F and both these are frequency. This L is for inductance. This C is in capacitance. The L is inductance is in millihenry or microhenry, and the C is in microfarad, nanofarad, or picofarad. Okay, resonance occurs when X sub L is equal to X sub C. So when we have this formula here, so 2 pi FL, which is our X sub L, when X sub L equals X sub C, 1 over 2 pi FC, if we break this down into its components, we eventually end up with this formula right here. This is the one you want to memorize. F equals 1 over 2 pi, the square root of LC. So where this came from is this right here. If we bring it down, if we bring F over, that's F squared equals 1. We bring over 2 pi L onto the right, and we keep C and 2 pi here. It comes out to 1 over 2 pi L, 2 pi C. We combine these two terms together, and eventually becomes F squared 1 over 2 pi squared LC. And if we want to take that square out, we square root both sides, and eventually we have F is 1 over 2 pi LC, the square root of LC. All right, so this is the only thing you have to memorize. You don't have to break it down, but that's where this comes from, this 1 over 2 pi the square root of LC. All right, so on to the next slide. Impedance matching is important so that the source can deliver maximum power to the load. So when we have a 50 ohm impedance on the transceiver and a 50 ohm impedance at the antenna, it delivers maximum power to the load. If one is slightly off than the other, then there'll be an imbalance, and that's called SWR, standing wave ratio. Ohm is the unit used to measure reactance. So just like resistance in DC circuits, the impedance, Z, is also called the ohm. Ohm is the unit used to measure impedance. One of the method of impedance matching between two AC circuits is to insert an LC network between the two circuits. So we can have a LC series circuit, LC parallel circuit. Here's a matching transformer. These are some examples that you can have. One reason is to use impedance matching transformers to maximize transfer of power. Devices that can be used for impedance matching at radio frequencies, you can use a transformer, a pi network. This is what you have in your antenna matching boxes, and a length of transmission line. So all these choices are correct. You can have transformers, you can have pi networks, and you can have a length of transmission line. In fact, we used a length of transmission line to tune in cavities for a duplexer for a 6-meter repeater one time. And we used the length of coax to do that. Okay, decibels. All right, 2 times the increase or decrease in power will result in a change of approximately 3 dB. So here's our decibel charts. Our decibels are log. So they're logarithmic. So 3 dB is approximately times 2. 6 dB is approximately times 4. 10 dB is approximately times 10. 20 dB is times 100. 30 dB is 1,000. 40 dB is 10,000. And so on and so forth, all the way up to 60 dB. That's 10 million. Here's the formula for that. It doesn't ask you in the test, but this is where it comes from. 10 log power over power 2. So we have positive 3 dB. If we talk about negative 3 dB, it's divided by 2. Negative 6 dB divided by 4. Negative 10 dB divided by 10. So if we're talking about plus dB, it's multiplied. And when we talk about negative dB, it's divided. So 3 dB is a common term that we use a lot. And that's times 2 if it's on the plus side. If it's minus 3 dB, it's in half. Okay, the total current entering a parallel circuit equals the sum of the currents through each branch. All right, so this was discussed a little bit in the technician exam. We have current flow from negative to positive. So if we trace out the current, here's one current. We trace out the other branch. We trace out the third branch. So we're going from negative to positive on each branch. And they all come back and they combine together. Here's branch 1, here's branch 2, here's branch 3. They all combine together into right at this point. So if you measure this, if you have a current meter right here at this point, that's going to be measuring your total current. If you have a meter right here at this point, you're going to be measuring total current. So it's the sum of all the currents through each branch. That's in a parallel circuit. Okay. Electrical principles. All right, 200 watts of electrical power are used if 400 volts is supplied to an 800 ohm load. All right, so what they're asking for is power. So if we look on our ohms law chart, power, they give us 400 volts, they give us 800 ohms. So we use our calculator, E squared R. So E, which is 400 squared, equals 160,000. Divide that by 800, and that will give us our power, 200 watts. Okay, another way to do it, 400 times 400 divided by 800. Okay, so did you see how I did that? If you have a standard calculator, if you don't have a nice scientific calculator like this, you can just multiply the E times itself. So 400 times 400, you get this E squared, and then divide it by 800. Or if you have the scientific calculator, E squared R, 400 is my square button, equals that, divided by 800. Now, a little note about scientific calculators. You notice that I put in 400 squared and hit the equals. Order of operation is really important on these calculators. If you just type in 400 squared and then divide it by 800, what it will do is it'll do okay, so if you remember, please excuse my dear Aunt Sally. It does parentheses first, exponents next, multiplication, division, addition, and subtraction. So you just want to be careful that with order of operation. So that's why I usually just type in 400 squared, hit the equals button. I have that number. Now I can just hit divide. It takes that answer, divides it, and I can divide it by my resistance, and it equals 200 watts. All right. Okay, so 2.4 watts of electrical power are used at a 12 volt light bulb that draws 0.2 amps. So what's given in the question is 12 volts and 0.2 amps, and they want to know power. So if we look up a power, P is equal to I times E. That's our magic circle, right? So if we want to find power, it's voltage times current. So that's really easy. Voltage, which is 12, times current, which is 0.2. Notice I'm in units, 2.4 watts. Okay, so here is a change in our powers of 10. So they're asking this a similar question. They're giving you current in milliamps, and they're giving you resistance. So we look at our Ohm's law chart. P is equal to I squared R. So now 7.0 milliamps. So if you're using the scientific calculator like this, second function exponent to the negative 3 squared equals that, times R, 1.25 e to the third. Okay, and it's going to give you the answer in units. Now, if you want to change that with this calculator, you go into second function and the scientific engineering. I like to put it on engineering units. That's 61.25 milliwatts. All right, so if you're using a standard calculator, when you multiply exponents, they add. So when we multiply 7 squared, then multiply that by 1.25, that's going to be 61.25 milliwatts. So here's the equation down here. All right. I'm going to pause the video at this point, and then I'm going to go into our AC sine waves, peak to peak, RMS, and all that.